horizon. Right, perfect. Exactly what 10th man says. But then it says your reading will be less accurate if you're not making a measurement from the level of the horizon or sea level. You'll need to correct that difference to find the true altitude of the object you're observing. Oh, why will you need to correct for that? What does that mean? The difference between your elevation and the level of the horizon is called dip. Even if you're at sea level, you still need to make a dip correction to take into account the difference between the horizon level and the height of your eye. Oh dear.
Oh dear is correct. Remember that time when I tried to explain this to you with the debate where I had to corner you on gems? Where I was explaining the horizon is just the limited angle and the true horizon is further? So are you actually going to answer the question now?
No, I actually feel
this
is the first time we've hold on, wait, just let me finish. This is probably the first time that we've actually spoken.
It's the fifth
And
time
what
I
actually thought that you were dumb, but I actually now just think you're just crazy because I'm listening to you now and you're just not taking anything in. Maybe it's the sixth time I've asked you. Maybe it's both Ranty, again, crazy and stupid.
How did you take perspective into account with this image, Ranty?
Oh my god.
I'm waiting. You haven't answered it. How have you taken perspective into account? So that's a no then.
That's you're too stupid to talk to.
So Kima, I hope this is recorded.
It is recorded, and you're just too stupid to talk to.
Thank you. So instead of actually explaining to your audience, instead of going to actually explain to your audience how you took a perspective into account, you just say, laugh and then sound stupid. Great rebuttal.
Yeah, you want me to. By the way, you want me to hold on. You want me to try and say how I took flat Earth perspective into this imaging in account? Yeah,
not flat Earth. Perspective. Perspective comes with optics in a distance. You should know this of all people.
I gave you both. I told you where eye level was.
You haven't told.
I told you where eye level was in both.
Where's eye level? But tell me where eye level is. It's not taking.
I literally told you it twice in the past. I went over it 2 times in the past 15 minutes. I told you exactly where eye level would be on a flat plane and where it would be on a globe. And you just stupidly waffled on and just completely either just didn't hear it or just stupidly ignored it. So you pick your point. Poison, which one was it?
Right, could you repeat what you said for me, please?
Okay, so you ignored angular size change. You ignored that the convergence point ramps up to...
Yes. Yes,
convergence point is the horizon.
You're right.
You ignored that you had to take perspective into account with this thing. You ignore that distance plays a part with this observation.
You claim that everything is crushing itself in the convergence point, and you claim that that's where eye level is. Well, you can be destroyed categorically just by simple mathematics, knowing that the height of the mountain in the background Great Orme is 207 meters, and the height of the elevation of the camera was at 270 meters. So just based upon that alone, you can actually destroy your entire argument saying that everything was crushed into the perspective crushing zone, whatever it is that you're claiming now, where everything seems to get crushed up into, and the horizon, the perceived horizon, is where eye level is. So we can literally just crush all that by the fact that Sandra just so happened to go to an elevation that was almost identical as the top of Great Orme. So you're too stupid to understand that.
So you see, Ranty, you get your eye level, which is the true horizon, and you get the apparent horizon, the one you actually see, which is the limited angle. Now, that horizon is lower than your eye level because it is at your feet. You are standing on the horizon's level and your eye level is above it. So that is their correction for the dip. So simply put, Ranty, you're just an ignoramus. Your eyes are at a higher elevation than your feet. AKA, that's what the dip is. Only optical, dude, not physical. Try again. Well, it's quite simple what's going on. Let's finish this off with a demonstration on us using a sextant.
This is a sextant, which is kind of the end of the evolution of a lot of instruments that were used to cite the altitude of stars in the sky. You typically use them for water navigation because you're seeing a physical horizon.
So you see, the normal globe believers still believe the horizon is physical, even though it's been debunked by the black swan. And Ranty's still claiming refraction. So Ranty, those two questions are still on the table for you, dude. Would you be so kind as to answer them for me, please? Thank you.
The sky is kind of like a dome, and you have the altitude of a celestial object, which is the angle from the horizontal. To however high it is. And then the other angle is called the azimuth, which is basically dividing up the horizon into 360 degrees. What the sextant does is it measures the altitude of celestial objects like the sun. So you get two images. This is a half silvered mirror, and you look through this telescope, and what you'll see is the horizon, number one. But number two is this mirror here is on a movable arm, which changes angle.
Notice the angle is a right angle. Look at that vertex. This can only happen with straight right angles.
The light from, let's say, the sun in this case will reflect off of this mirror and will then reflect off of this partially silvered mirror, and I'll see the image of the sun brought down to the horizon. And then by manipulating this lever arm and this little veneer screw, what I can do is get the altitude of the sun to a precision of about an arc minute, which is 1/60th of a degree, which represents 1 nautical mile of uncertainty. So that's the kind of precision with good practice you could get with a sun sighting. I adjust it so that the lower limb of the sun, that is to say the lower part of the image of the sun, is just touching the horizon. This is a coarse reading in degrees, so you can see that we ended up with about 36 some odd degrees, and then this little drum here tells you how many arc minutes. What I now can do is do a few corrections. One is for the refraction of the atmosphere. One is for my height above sea level. And something called an index correction for my instrument. And then once I get the true altitude of the sun by making these corrections, I can basically do a little correction and figure out where my line of position is.
So it's very simple. To get the trigonometry to work, the horizontal has to be a 0 degree, aka flat plane. Thank you very much for watching.
All going uphill at a fairly exponential rate. So it's good stuff. Subscribe today to Flatzoid.